So, welcome back to week two. This is the first lecture for section 5.3, which is electron configuration and periodic properties. It's our last section of chapter 5, so we'll be wrapping up chapter 5 here this week. And really, what the title of the section should be is periodic trends. So, we're going to see what kind of trends there are with different types of quantities that we can measure going down a group in the periodic table and going across a period. Okay, so for today, we're going to look at two, like I mentioned, atomic radii and ionization energy. Okay, so let's first define what atomic radii is. So it's really, in layman's terms, the size of the atom. Okay, specifically, as you can see here, 1/2 the distance between the nuclei of identical atoms that are bonded together. So from the center of the nucleus to the outer portion of the electron cloud. We do that with two atoms bonded together because one atom, that outer portion of the cloud, is so fuzzy. Remember, that's just an area of negative energy where the electrons are, that when we have two atoms together, we can measure nuclei to nuclei, or sort of estimate that, and then take half of that to get our actual size of the atom. So here I'm going to put up a graphic, and this graphic has both the groups. Remember, those are your vertical columns, and your periods. These are these horizontal rows. These specifically are for groups 1 and 2. So your alkali metals, your alkaline earth metals. Group 13. So what we don't have in here is the D block. Okay, so we jump to group 13, which is the boron group, group 14, which is the carbon group, group 15, which is the nitrogen group, group 16, which are the chalcogens or the oxygen group, 17, the halogens, and 18, the noble gases. And just take a look at that for a minute and see if you can see any trends in terms of size on this abbreviated periodic table, which really, when we deal with groups 1 and 2 and then 13 through 18, we call those the main group elements, or the S and P block. And hopefully you see one trend. As you go down a group, okay, the atoms tend to get larger. Okay, they tend to get larger as you go down the group. Okay, hopefully the other trend that you realized or that you observed was as you go across, whoops, I jumped back, I'm sorry. As you go across the periodic table, so across periods, they get smaller. Okay, so that's a trend. So you can make some predictions on the size of atoms depending on what group they're in and depending on what period they're in by their location. So if I would ask you, without the use of a periodic table that has these sizes on it, which atom do you think would be larger, sodium or rubidium? Okay, which here's sodium here and here's rubidium. And if you didn't have this periodic table that had these sizes on there, you would use the trend, well, atoms tend to get larger as you go down a group, and you could say, well, rubidium is going to be larger than sodium. Also, using your period trends, if I asked you, well, what atom would be larger, magnesium or chlorine? And hopefully, using your trends just on a normal periodic table, you would be able to say, well, magnesium would be larger than chlorine, because the trend is as you go across the periodic table, atoms tend to get smaller. But let's take that a step further. Let's look at really why that is. Why do atoms get larger as they go down a group? And why do atoms get smaller as you go across these periods? Okay, so here's your period trend, and this we're going to kind of go through the reasoning right here. So you do see a gradual decrease across periods. So they get smaller. And remember, as you're going across there, you're actually adding electrons. So it might be thought, well, maybe they get bigger as you go across there. But as you go across that period, as you add an electron, you're also adding a proton. And the electron that you place in that energy level is the same energy level as one of the elements in the first portion of that period. So the nuclear pull has more of a factor in size than does adding the electron. So you can see here, increased positive charge of the nucleus pulls the electrons in closer. Therefore, they have a smaller atomic radius. And really, what we say is effective nuclear charge. You're pulling on electrons that are in the same energy level, so this nucleus pulls those in tighter. Okay, so here's our group trend. And as you can see, with your group trend, gradual increase going down a group. So atoms get larger as you go down a group. And as you can see there, electrons occupy higher energy levels. You're adding a whole new energy level every time you go from one atom to the next going down a group. For example, with sodium, that is 3s that you're dealing with there. Where potassium, which is the next element, is a 4s. So you're adding a whole new energy level. Therefore, the atom tends to get larger. Okay, so what I'm going to ask you to do in the future is make some predictions based on the trends without really this in front of you where it has the actual sizes of the atoms. Okay, you use your trends to make predictions. All right, so let's move forward a little bit more to our next trend. Our next trend is called ionization energy, or abbreviated IE. And this is closely related to atomic radius. It's a different concept, but the reasoning is very closely related. So the ionization energy is the energy required to remove one electron from a neutral atom of an element. Okay, and when we talk about the first electron to be removed from a neutral atom with no charge, we talk about IE1. And you can see that little subscript 1 right here. IE1, first ionization energy. So you're taking away an electron from a neutral atom. This always takes energy. Okay, it's endothermic. Energy is going in to pull that electron away from the nucleus. Okay, and we want to look at, well, how does that trend appear on the periodic table? Just real quick, a little bit of terminology here. An ion, remember, that's an atom or even a group of atoms that has a positive or negative charge. And that is coming from a gain or loss of electrons. With ionization energy, we're always looking to form a positive ion because you're removing a negative electron. So let me throw this up here for you, and you can take a look. This does include the D block and the F block down here, the lanthanides and the actinides, and see if you can come up with any trends as you go down a group and as you go across the periods. Okay? And hopefully you see the same trends that I do, and the trends are this. As you go down a group, ionization energy tends to decrease. Okay? And the other trend that I see here is, for the most part, and there's a few exceptions here, but as you go across, especially if you look at the value here compared to the value here with sodium as compared to argon, ionization energy increases across a period. And that trend in terms of increase decrease is actually the opposite of atomic radii, but the reason for the trend is the same. Okay? Here's another way to look at this. Just a little graph of ionization energies. And this is across a period right there going up this way. And then this would be going this way, would be like group wise. Okay? You can see here there are a couple of exceptions that are very similar in each group. And that has to do with electron configurations. So this is, 3s1, and this is 3s1. Excuse me, this is 2s1, 2s2, and then this is 2p1. So it's a little less energy to remove a p electron. This happens to be p3 versus p4, 2p3 and 2p4. Remember Hund's rule where we fill up one with each, then we go back and pair up? The paired up electron's a little bit easier to remove than one in each. Okay, and they're called discontinuities. Don't worry too much about those. I just want you to have the main trend. So here's some reasoning. So our period trends. As we saw, ionization energy increases across the period. So what that means is an electron is more difficult to remove as you go across the period. So over on the right-hand side of the periodic table, those electrons for those elements are difficult to remove. So why is that? Well, it's the same reason that atoms get smaller. as you go across the period. That effective nuclear charge. It pulls those electrons in closer, it holds them tighter, so you need more energy to remove them. Okay? And here's your group trend. And for the most part, we saw that ionization energy decreases down a group. So what that means is electrons are easier to remove toward the bottom of the periodic table. And the reason is, again, those outer electrons, remember, we're adding energy levels as we go down from one member to the next of a group. They're further from the nucleus. And those electrons are easier to remove. And one thing that we do, this is a new term I didn't use with atomic radii, but it's called the shielding effect. And once you get a lot of electrons on the inner portion of the atom, it shields the positive charge of the nucleus. So the nucleus doesn't have as much effect on those outer electrons because they're being shielded by those inner electrons. And those inner electrons are called the core electrons. Okay? So these are your two trends. All right? There's going to be three more we're going to add tomorrow. So make sure that you get these down. What I'm going to ask you to do is make some predictions over size or over ionization energy from location on the periodic table.